All right, so now we're going to look at what happens when you have repeated observations and how to relate it to maximum likelihood estimators. Okay, so so say you're given a probability distribution for a certain random variable, you could take multiple, independent measurements from that, right? So, so you could, um, so you consider basically independently observed data. Let's call that x1 to xn from the same probability distribution. Let's call that p of x with some parameter theta. Okay. And you want to do this in an exponential family. And the goal is to estimate the parameter theta, right? So with a view towards estimating theta. Okay. So you can ask yourself, well, what is the joint probability density function? It's like these observations. And because you have something which is independent, it's like and identical, it's like you have IID data, then the joint probability density is just given by the product, it's like of the individual probability densities, right? So p x1 to xn with the same parameter theta, right, is given by the product from I equals 1 to n of the probability of xi with that parameter theta. Okay. So you can ask, it's like, starting with this initial probability distribution p of x comma theta, how, the fact that you have repeated observations, like for the same distribution, changes the geometry, it's like of that, of that space of probability distributions. Okay, so how does the geometry of M change with repeated observations? Okay. All right. So you could, for example, consider just the average, it's like of the observations. So consider x bar. It's just the sum of the observations, it's like divided by n. Okay. Then I can rewrite, it's like this probability distribution the following way. So then Pn x bar theta, okay, it's just p of x1 to xn theta. So what I'm trying to do basically is that I'm trying to ask, well, if I take the average of these observations and I think of that as a single random variable, right, how does this relate to, how does this, the geometry of this distribution relate to that of the original one, right? So this is equal to the exponential of n theta times x bar minus n phi theta. All right. So the point, if you will, is that the probability density for the average of x bar has the same form as that for just a single instance, if you will. Except for the fact that that x is replaced by x bar. Okay, and this term here becomes n times as large, right? Okay. So in particular, if you recall, it's like, this stuff here doesn't matter so much as this term here. This term here is the convex function which generates the corresponding Bregman divergence, which then induces, it's like this, dually flat geometry. It's like on the space of distributions, right? So that's the thing to keep in mind, and that's, in some sense, it's like what's changing, it's like as you do these repeated observations. So this basically implies the following, that the convex function in question becomes n times as large, right? And as a consequence of that, things like the Kl divergence, it's like becomes n times as large. So Kl divergence and the Riemannian metric right also become n times larger. But the dual affine structure F doesn't change. So so the point is that because of the fact that the dual affine structure doesn't change, it's like you can still use the same coordinates theta. Even though you're taking multiple observations for your statistical inference. Okay. And then the other remark is that the binomial and multinomial distributions are exponential families. Derived from your sort of 2 probability simplex and n probability simplex by multiple observations. Okay, all right. So let's see it's like what the consequences of all this is. So let's say we have M, which is an exponential family. And you consider a statistical model. Okay, so S is the set of probability distributions. Which is embedded, it's like in this manifold M, okay? It's a submanifold. Okay, and then with parameters. So the space of statistical models is parameterized by this U. Okay, U is going to be U1 to UK with the property that K is less than the number of observations you've made. Okay, all right. And of course, it's like you might expect that. So this is more or less saying that this space of this statistical model space is like a k-dimensional submanifold. It's like of the exponential family, all right. And you're taking, it's like more observations. It's like the dimension. It's like of that manifold. So you're at least in a situation where conceivably it's like you have enough information to then uniquely specify a point that's like on this submanifold, right? Of course, if you take less measurements than the dimension of that submanifold, it's like then, it's like you're clearly not going to get a unique solution. Okay, all right. So what happens now, right? So since this is contained in M, okay, so since S is contained in M, this set of possible statistical models is contained in the exponential family, right? So the E coordinates of these probability distributions of Pxu, right, in M are determined in terms of U, right? Okay, which is to say that, so the E coordinates were the theta coordinates, if you will. So this basically means that I can write the theta coordinates, right, in terms of these coordinates on this submanifold, right, or the parameters on the submanifold. Okay, so let's say that I'm given independent observations. So if I'm given n independent observations, I would like to estimate that, right? So x1 to xn, I want to estimate U, right, based on them. Okay, so let's see how you go about doing this. So the observed data specifies the distribution on all of M, right? Such that its M coordinates given as follows. So eta bar, right, is 1 over n, the sum of the xi's, and that is of course just x bar. Okay, so this is the observed point. Okay, then you can ask, what is the Kl divergence? It's like from this observed point to, it's like to a distribution. It's like in S, right? So the Kl divergence from the observed point. So again, this is the dual coordinate, and I'm just letting it be x bar. So this is sort of similar to the case we looked at before when we were talking about the maximum entropy principle, if you recall, right? And the trick, if you will, is to think of the dual variable. It's like as this observation, and because of the way it's like the Bregman divergence and in particular the Kl divergence can be written, you can then take advantage of that formulation. Okay, all right. So where was I? So the Kl divergence, it's like from the observed point, which is just the mean, right, to a distribution that's called at p x mu, right, in this space of statistical models S, right, is just given by the divergence, the Kl divergence, right, from theta bar, right? So this is the primal coordinate associated with this dual coordinate, right, to theta, which depends on u, right? And this is the thing, it's like which is an S, which you're trying to figure out. Right, so this is sort of a trick. It's like we've seen before, again, in the context of this maximum likelihood estimator, right? You think of the observed data. It's like in this case, the mean. It's like x bar as the coordinate of the dual variable. You look at its corresponding primal variable as a point, right? This is sort of the point which you're then trying to find some sort of closest point on the space of statistical models, right? Right. Okay. So as I said, it's like theta bar is the theta coordinate, which corresponds to the dual coordinate eta bar, which, if you recall, is the observed point x bar. Okay. So, okay. So let's look at a simple case. It's like which is just Sn. So consider the case of Sn. So the observed point is given by this probability distribution p bar of x, right, is equal to 1 over n sum from I equals 1 to n of delta x minus x sub I. Okay. So modulo sort of a constant term, right? Minimizing this Kl divergence. is equivalent to maximizing the log likelihood. Right, which is given by the sum from I equals 1 to n of log p xi comma u. So the point basically is that this maximum likelihood estimator is corresponds to a projection, if you will. So the maximum likelihood estimator just corresponds to minimizing the divergence by M projection, which is this mixture projection, if you will, of this given probability distribution P bar of x, right, to your space of statistical models. So again, the bottom line is that maximum likelihood estimation is related to M projection. Okay. All right. So so again, it's like what you've seen is that many of the kind of things it's like one does in statistics, which is to look at observations, data, and then from that do some sort of statistical inference to figure out which is the most likely element. It's like in some sort of space of statistical models. It's like which represents, it's like our best guess as to what the actual distribution which you're sampling from. A lot of those things are related to various notions of projections, either primal or dual projections or the E or M projections. So yeah, so anyway, so that's just a way to illustrate that many, again, of the statistical concepts which we are aware of, right, have an interpretation in the context of information geometry. So let me just stop here for now.